Hey guys, welcome to class. It's Mrs. Brunk here. In today's lesson, we're going to be taking the strategies we've been reviewing on how to solve systems of linear equations, and we're going to use it to apply it to some real life situations. And so our learning goal today is and I guess our essential question really is, how do you use systems of linear equations to model and solve real life problems? Because in the end, that's exactly why we study mathematics, is to apply it to real life. So creating linear system models from verbal descriptions. Often a company will charge a startup fee for its services, followed by a monthly or per unit cost. This can be written as a linear function in slope-intercept form. When the cost of the same services from two different companies must be compared, the variable amount of each must represent the same thing, and both models should produce values with the same type of unit. For example, if one function models yearly income in terms of thousands of dollars, and the other function models monthly income in terms of hundreds of dollars, the comparison will not be accurate. So basically, we just want to make sure we're comparing apples to apples and that the variables represent the same things in the same units. So as we write our equations, these are good, and for our system, we just have to keep those things in mind. So if we want to be able to compare to companies, to offers, to whatever, we have to be comparing like units. So here's an example. We'll jump right in. Determine when the cost of two services will be the same amount and what the price will be. Video streaming services, Atomic Stream, charge $10 for membership and $1 for each movie download. Blitz Video charges $15 for a membership and 50 cents per movie download. How many movies would you need to download for the services to have identical costs? And what is that cost? So the two functions, well, the first one, so say we call the first one be A for atomic. So we've got A. So when I write real life systems, since I'm obviously not going to be using graphing to solve these, I like to use variables that represent the situation. And so since I'm talking about the cost of streaming, I'm going to call the cost C, or the charges. And then I'm going to call the other thing, which is the month, our movies, we'll call that M. So, or videos. I guess you could use, I guess it's for movie downloads. So we'll go ahead and use M. So for M will be for movies, and then the cost, the charges, will be C. So atomic, I could describe like this. We have a starting amount of $10, which is like your y-intercept, of $10, and you're adding $1 for every movie that, and you can write it as $1 if you want, or just leave it as 1 in this case because it's $1 per movie. Now Blitz would be the cost is equal to $15 plus 0.50 times M, so 50 cents per movie. So then what we could do is, now we've got this nice simple system, we could pick one of our methods. This is uniquely set up to use substitution because see how they're both solved for C. So all I have to do is now take what this equation says C is equal to and set it equal to the other. So in other words, since they're both solved for C, I just set them equal to each other. And then I can solve using my algebraic methods. So just to kind of save time in this video, because this is a really easy equation to solve, I'll just tell you that when I solved this, I got that M was equal to 20, so 20 movies. So I got, let's see, M equals 20. And so that cost, so the cost of each service is the same when 20 movies are streamed. And that cost, if I wanted to know what that was, I could just simply take the 20 and substitute it into any one of the equations, or either one of the equations, and find out that that cost would be, like for instance, the top one is easiest, so it's 10 plus 1 times 20, which would be $30. So the break even for the two, when it would cost the same, is $30 and 20 movies. So Atomic Stream is more affordable for customers who stream blank movies a month. Well, if you think about the Atomic, there's a smaller startup cost, but they charge $1 per movie. So when they're under 20 movies, excuse me, that Atomic is cheaper because you don't have to pay that additional $5 extra for the membership up front. So it's going to be more affordable for customers who stream less movies a month, less than 20. I guess we could put in less than 20. And Blitz Video is better deal for people that stream more than 20. They didn't really give us a lot of space for this, but more than 20 per month. Okay, so once we get the equation written, then we're just kind of falling back on our strategies on how to solve. Whether it be substitution, whether it's elimination, certainly probably not going to be graphing. All right, let's take a look at some more. So determine when the cost of 2 services will be the same amount and what the price will be. One cable television provider has a $60 setup fee and charges $80 per month, and another cable provider has a $160 equipment fee, which is like it's maybe different than the setup, but they charge for the equipment, but it's still a fixed rate, and $70 per month. And we want to determine when the cost of the 2 services will be the same amount and what the price will be. So go ahead and pause the video now and write and solve an equation for this. And you can tune back in to see how you did. So again, you're going to write a system and solve it to answer the question. Pause the video now. Okay, so our system would look something like this. Cost, if you use the variables I did, but the cost is equal to 60 plus 80M. Or you could also flip that around and say 80M plus 60. But just sort of, the way that this is given to you, it's almost smarter to write it b plus mx instead of mx plus b, to putting the y-intercept or the starting point first. And then the second one, 160 plus 70m. Solving that, I used substitution, and I got that m was 10, and then that means that the cost at 10 months for both services would be $860. Now again, you can answer questions like, well, when would it be less expensive to go with the second company? Like, well, if it would be, if you are going to go for more than 10 months because now you've recouped that original extra $100 startup fee. And so that would be cheaper after 10 months. But if you plan to just keep the service for under 10 months, then you would, go with the first cable provider. So. And let's just take a look at just setting up one more. We won't actually solve this one. We'll set this one up together. So the Strauss family is deciding between 2 lawn care services. Green lawn, so we've got one that's called GL, like Grand Ledge. And then we have one that's called Yard Guard, so YG. And Green Lawn charges, for their cost, is $49 for startup and $29 per month. And Yard Guard charges $25 as a startup, and then they charge more per month though. So there's always a trade-off there. Like one costs more to begin with, but it's cheaper per month. And so really you just have to decide where the break point is. And then once you know that, you can make your decision based on how long you choose to use that service. So again, we won't worry about solving this, but just setting it up is, the main battle, because the algebra part of it we've been working on, so we can do that no problem. So we're going to look at another type. See, these both have been set up in slope y-intercept form, and at the end of the lesson, we're going to bring in a couple questions where maybe we might have equations in standard form, which is also very common in everyday problems. So, but in this next part of the lesson, we're going to look at what about if instead they're not specifically stating like the startup amount and the per monthly cost for something like this, but let's say they instead are giving you some specific cost examples, like this is what this person paid and this is what this person paid, and so it's basically like they're giving us some specific instances, and we have to take that and decipher what that means about what the startup costs are and what the per monthly fee is from a table of values. So sometimes there's not enough information to model an equation. Businesses may have a table of rates posted to explain their pricing. So to compare the cost of items or services from two or more businesses, table entries can be used to create and solve a linear system. So two garden supply companies deliver mulch according to the following table. So it's like this column right here is the mulch. It's how much they're ordering in cubic yards. So this would be kind of like our x coordinates or our independent variable. And so it's like they're just combining two tables. So there's one table like right here that is for one company right here. And then there's another one if you take the first and the last and put those together. So like if I took this with this one, that would be another table. So we've got the, basically we have some ordered pairs in this table. So they just kind of say, well, with the one company, if you want 1 cubic yard and you go to Yard Depot, it's going to cost you $60. If you want 2, it's going to cost you $90. If you want 3, it's going to cost you $120, and so on. So just looking at that first company, so just kind of ignoring this part for right now, just looking at those, you can see that as you increase 1 cubic yard of mulch, you go up $30. So each time you're going up, hold on. So we know that with this company, we know that the cost is going to be $30 per cubic yard. So whatever you want to call that, like mulch, we call it, I guess, M for, you can just say that M represents a cubic yard of mulch. But then how much there's obviously built into that first cubic yard some sort of delivery fee because they charge you $60, but for each additional yard you get, they're only charging you additional $30. So if you work backwards, let's say you went backwards and say, now I have 0 cubic yards. And I know that doesn't really make sense because then they wouldn't be coming to deliver anything. But if you went back $30, now you're at $30, right? So we went in the reverse. We took and used that per yard mulch cost going backwards. We could see that there must be a delivery fee of $30. So it's just kind of like working backwards to find the y-intercept. Remember, the y-intercept is when the input value or the x value is 0. So we're just kind of working backwards to find the 0 term, in other words. So we could do that exact same thing now for the other company. We can see, okay, so moving forward from when you have 1 yard to 2 yards, it goes up by, looks like, $25. And then again, from the next one, you go up $25. And then increasing another $25. So that means the per yard cost at this company is $25 per yard. But then, of course, there's built in some delivery fee. So if you went backwards now, instead of going forward 25, you went backwards 25. So you'd have to take 25 away from 80, you get 55. So that $55 must be the delivery charge. And then you pay $25 for each additional yard of mulch. Again, it's really just a matter of if they give you this, pricing chart, you just have to work backwards to kind of essentially see what that is made up of. It's made up of a per yard cost as well as a delivery fee that's kind of like a fixed amount. You pay no matter how much you get delivered, and then each additional yard you get, you're adding on so much more. So there's a system you could then solve. Now another way you could do this is back to when we first started looking at writing equations for lines. You could have taken a pair of points like we did down here for Yard Depot. We took 1 cubic yard is 60, 2 cubic yards is 90. You could calculate the slope, and you could go through writing the equation for the line using slope-intercept form. You could also do that here with the lawn and garden and do the exact same thing. But most of these are pretty easy to decipher just by looking at the table and the trend, figuring out the slope by looking at the table, in other words. So let's try this with another example. So this one shows canoe rental prices for 2 companies. There's Canoe Depot. So let's see, we're going to describe Canoe Depot and then paddle and oar. So P and O. And we'll just describe them and see how they price it, and then See if we can figure out when it would cost the same if we want to solve it. I mean, we probably won't solve these now just to save time in the lesson, but we'll just set them up because the solving part, that's the part we probably have, mastered by now. So time in hours it's 1 hour. If you rent for 1 hour, it costs you $14. But if you go to a second hour, now it's only $19. And then a third is $24. So what's happening here is they're adding $5 for every hour that you add on. Okay? So in theory, if you canoed 0 hours, you went backwards $5, it would actually be $9, right? So, I mean, I know that it really doesn't make sense because if you went 0 hours, you shouldn't be paying anything. But that's like your y-intercept. When you write your equations, you need that, that's that sort of fixed built-in upfront fee, and then the additional per hour fee is $5 for each hour. So that would be, for that company, the cost, let's say we call it, again, cost or whatever, it's going to be $9 plus $5 per hour, or $5 an hour plus $9. Now the other company, on the other hand, you can see that that first hour is significantly more expensive, but they're only going to charge you $3 extra for each additional hour. So working backwards, if we went back to the 0 hours, it must have been $17 for that starting amount. So they charged a $17 flat rate, and then for every hour, it's a $3 charge. So even for that first hour, they're charging you $3, but it's $17 just to get in the canoe, and then $3 for that hour. And then each additional, they charge you an additional $3. So again, we could go ahead and solve this. That's, you'll get to do that in your homework practice. But just writing that is really, I think, the big challenge now at this point is just the new skill is just writing our own equations. Okay, so here's one for you to try. So we'll have this be your you try question. So pause the video, just write the system. You don't have to actually solve it. So just write a system and tune back in to see how you did. Pause now. Okay, so a system that would work for this would be, for the first one, I used C and P for cost and P stone, or I guess it's in cubic yards, you could use Y or whatever. But C is equal to 40 plus 35P. And that one's got a much higher upfront, but it's only $35 per yard. The other company, $5 is their kind of startup fee, and $40 for every cubic yard. Okay, so we've looked at, all of the systems we've looked at so far have been types that would be perfect for slope y-intercept form equations, and therefore you solve them by substitution because they're both, written in terms of a single variable. The final 3 examples that we're going to go over are going to be ones that are going to produce equations that will be, we want to use our elimination method because they're going to be ones that are in the form of AX plus BY equals C, or standard form. And that's because not every real-life situation lends itself to that type of slope-intercept form equation. There's not always like a starting amount and then a per unit increase or whatever. Sometimes we're just looking at combinations of 2 things, like say you're purchasing shirts and pants for a uniform, and you're buying combinations of those 2 things. And you have a certain amount that you have to spend. So that's called a linear combination scenario. So here's some examples of that. So Marcy bought a total of 20 used books and CDs during a yard sale for a total of $54.50. If books cost $1.50 each and CDs cost $5, how many of each did she buy? So instead of there being like a cost and then like a certain number of items, instead there's 2 different items we're buying. So there are books, let's say we call them B for books, and then we have C, say for CDs. So instead of having like 2 companies that we're comparing or whatever, we just have 2 facts that we have got to write using these two variables. So the first fact is this fact. Marcy bought a total of 20 CDs and books, right? So we don't know how many of each, but she bought a total of 20 items. So that would actually be a really simple equation to write. We would just say the number of books plus the number of CDs that she purchases is 20. Okay? So you can see that both the variables are on the same side. That's a linear combination or a standard form equation. Now the second thing we know, so this was the total items. This is the number of items. So that's our first fact. And the second fact is the cost, the amount of money that she spent. So she spent a total of $54.50. Oops, running out of space there. And that was made up of purchases of books and CDs. Now for every book, then she paid $1.50. So it'd be $1.50 or 1.5 per book. And it was $5 for CDs, so that would be 5C. So that's our second fact. And remember, if we have two unknowns, we need two equations. So like when we needed to find x and y, we needed to have two equations. We want to find b and c, we need two equations. These are just different kinds of equations, and they're the equations that really lend themselves to do elimination. So for instance, on something like this, I might want to solve this by, say, I multiply the whole top equation by, say, -5, because then, let's see, that would make, let me rewrite them over here. I didn't leave myself a whole lot of space here. But that first one would be -5b plus -5c equals -100. And then I have 1.5b plus 5c equals 5450. And now I could use my elimination method where I add the two together. So now these are going to cancel out my c's. I'm going to have a -3.5b. And that's going to equal, let's see, is that 40... -4550. Oops, I'm running out of space there, so hold on. Oops, it's a -4550, and then all I have to do is divide by a -3.5, and that's going to tell me that B must be 13. So we've got the number of books now, and then remember that she bought a total of 20. Right here, right? 20 items. So if I take that 13 and substitute back in, I'll find out that the CDs, she must have bought 7, because already 13 items have been purchased in their books, so the other 7 must be CDs. So this is the type where you're going to use elimination to solve. Let's look at another one. Landon babysits and works part-time at the water park over the summer. 1 week he babysat 3 hours and worked at the water park for 10 hours. And made $109. The next week, he babysat 4 hours, or wait, oops, I cut that off, so I don't know what that says. Uh-oh, let's see if I can figure out what that one is. Just a second, I'll have to look that up on my paper. Okay, so that's supposed to say I cut off 8 hours, and worked at the water park for 12 hours and made $177. How much does Landon make per hour at each job? So he's got 2 places he's working. He's babysitting, say we call that B, and water park would be W. Okay, so always choose to use variables that represent the real life situation. It makes things so much less complicated. You don't have to be so tied to X and Y. B and W will work fabulously on a problem like this. So as you kind of look through, we have to come up with 2 facts, right? And it's not 2 companies like with the prior ones we looked at, but this time it's 2 weeks worth of working. So we basically have week 1, and we have, oops, actually I'm going to use this space right here. We have, because I don't want to run out of space again, so we have week 1, and we have week 2. And then we're just going to write 2 facts using this data from week 1 and week 2. So week 1 it says he worked 3 hours at babysitting, so 3B. And 10 hours at the water park, so 10W, and made $109. So there's an equation, standard form equation. The next one, he babysat for 8 hours, so 8 hours babysitting, and worked 12 hours at the water park and made $177. So this is another system that's in standard form. And so say we want to use elimination, this is going to be one of those ones where it's a little harder to get the coefficients of either the B or W to be the exact opposites. So maybe you decide, okay, I'm going to take this top one and multiply by 8, and I'm going to take this bottom one and I'm going to multiply by, say, -3, okay? And then see what happens. So we'll just rewrite this real quick. So let's see, I've got 8 times 3B, that's 24B, plus 80W, and then 108 or 109 times 8 is 872. And then the bottom one there will become -24B, which is exactly what we wanted it to be because we wanted those to, cancel out, -24B. And then we have, let's see, -36W. And then 177 times -3 is -531. And now all we have to do is add the equations together. The B's, of course, will cancel. The 80 minus, or plus -36 is 44W. And the 875 plus, that was supposed to be a -531 is 341. And all we have to do now is divide by 44. And we find out, oops, I did something wrong. Hold on just a minute. That's not right. Actually, that is right. I don't know why that bothered me, that it was $7.75. That makes perfect sense. That it was the wages working at the water park were $5 or $7.75, which is what we're trying to find, how much they make at each place for those hours. And so the water park is $7.75, and if we wanted to find how much that Landon makes babysitting, we just simply have to take that $7.75 and plug it into one of the equations, whether it be one of the originals or these new ones. I wouldn't choose the new ones because they have bigger numbers there for coefficients, but say we take that, plug it in here, that makes 10 times 7.75. So we make $77.50 doing the water park job, and then that means if you subtract that from 109, that leaves $31.50 to make from babysitting, which means babysitting must make $10.50 an hour. So $10.50 an hour, and again, these are per hour rates. So again, once we get to really getting the system down is the key here, and then of course the solving will be a little bit more the complicated in terms of the solutions than we've looked at yet, because now we're talking about real life problems. But you have a calculator, so shouldn't really be a big deal. So this leaves us with one last one that we're going to do together. So this one tends to trip students up a little bit, anything that has to do with money. So that's a good one to do together. I won't leave you as you try one. So it says Kent has a collection of pennies and nickels. Okay, so these are the two things. We have combinations of two kinds of coins that have a value of $1.98. The number of pennies he has is 5 less than twice the number of nickels. How many of each coin does Kent have? Now, I'm going to be honest. You read that through the first time, and it seems really overwhelming. Okay, but so you just kind of come back and you just establish what are your two unknowns. We don't know how many pennies, P, and we don't know how many nickels, N. Okay, but we do know that they have a value of $1.98. Okay, so we have two things we're dealing with. We have the value of the coins, and we also have the number of coins of each coin. So, and we have a statement that tells us how they relate to each other. So we have the number and we have the value that we're going to write two facts for. So first of all, the value. When I think about pennies and nickels, okay, and how they add up to $1.98, it's based on the value of each one. And a penny is worth a cent. So I could write 0.01, that's what a penny is worth, right? Per penny. And then nickels would be worth 5 cents, so it would be 0.05 N, and that's going to equal $1.98. Now that's one option. Now a second option we could go with is, instead of doing it in cents, we could take that $1.98 and move it over from dollars to cents, and it would be 198 cents. And if we did that instead, it just makes a little easier equation to work with, because now instead of 0.01p, we just say 1 cent per penny plus 5 cents per nickel is 198 cents. Okay? And that's not going to affect our solution at all, but it's much easier to work with numbers like that. So that's what I would always encourage you to do when you're dealing with cents like that, is just change, if the value is given in dollars like that, change it to cents by multiplying it by 100. And then I'd use that one instead. Now the number of coins. So it says that the number of coins, number of pennies, so pennies, P, oops, let me change my color real quick, pennies is 5 less than twice the number of nickels. So how do we say 5 less than twice the number of nickels? Well, twice the number of nickels is 2n, and 5 less than that would be to subtract 5. Okay, so here's our system. We have 1p plus 5n. Oops. Let's get that in there. We fix that. 1p plus 5n equals 198. And then we have p is equal to 2n minus 5. So to solve this, I'm going to use substitution, because I could just take this right here, and wherever I see p, I could put that in its place. Well, here's another reason why this is nice if you use 1 instead of 0.01, is now when I substitute that back in, I don't have to multiply by 0.01 and make even worse numbers. So I could substitute that in. That makes 2n minus 5 plus 5n equals 198. Again, I'm just taking that, substituting in. So to write a new equation that only has n, add my like terms together. So I have 7n minus 5 equals 198. If I add 5 to both sides, that makes, let's see, 203. And 203 divided by 7 is 29. So that means the number of nickels is 29. And then all I have to do is figure out how many pennies by substituting in. Now, I personally think it's probably just easier to, I guess it doesn't really matter now that we've written the simpler value equation, but I just personally think plugging it in here is easy because it's already solved for p. So I just say p is equal to 2 times 29, which is 58, minus 5, and that makes 53 pennies. So I have 53 pennies, 29 nickels, and just to double check, I'm going to go ahead and put it in my calculator and say, okay, if I had 1 cent and I had times 58 pennies plus 5 cents times 29 nickels, and if I substitute, oh, I did something didn't turn out right. Oh, not 58, sorry, 53 pennies. Sorry, 53 pennies. Oh, then I got $1.98. So it checked when I substituted back in, and so I know that now there's 29 nickels and there's 53 pennies. All right, well, so that does it for today's lesson. I'll see you in class.